In today's lesson, we are going to go through an investigation. We're going to be looking at paper folding. So we're going to be going through an investigation to look at a specific type of function. So in the previous lessons, we've looked at linear and quadratic functions. We're going to be looking at a different type of function here. So what we're going to do, start off with a prediction. How many times would you need to fold a piece of paper in half for the thickness to reach the top of the school? Or 15, approximately assume like 15 meters. So come up with a prediction. Next, another prediction. How many times would you need to fold a piece of paper in half for the thickness to reach the top of the CN Tower? Assuming that it's 457 meters. And finally, how many times would you need to fold a piece of paper in half for the thickness to reach the moon? The moon being 384,000 kilometers. Again, come up with a prediction. Then think about how many times can you fold a piece of paper. So how many times do you think you can fold a piece of paper? And again, in class we will be going through this. If you have a piece of paper available to you, feel free to go through, fold it, see how many times you can fold it. Again, you want to fold it so you get nice even layers, not where it's kind of bunched up or not folded over completely. Would that change given the size of paper? Right, so try to do it with a regular standard piece of paper, a legal size piece of paper, and maybe if you have any, maybe chart paper or a larger sheet of paper, maybe some wrapping paper. See how many times you can fold it in half. How thick would the paper be if it were folded 30 times? So again, most of this is an investigation for you to work on your own and to try going through it, but I will kind of give you some tips or at least get you started so that you should feel comfortable going through it. So if I were to fold it 30 times, how thick would it be? And I'm telling you that a piece of paper is 0.01 centimeters thick. Right, so if I have a slice of paper here, 0.01 centimeters. So how thick do you think it would be if it was folded 30 times? Well, I'll let you take a guess, and we'll skip past all of this, because again, you can work through this on your own, but I'll give you some hints on where to start. So let's assume we have a picture. So if I have one slip of paper, like how we just drew, there's 0.01 centimeters. If I fold that on top of itself, essentially now there are two layers. So now this is 0.02 centimeters. So this is 0 folds. This is 1 fold. For 2 folds, again, that gets folded on top. The initial layer. Oops. So almost something like that. So now I have 4 layers of paper. So 0.04 centimeters. And again, we can keep on drawing these pictures for the next fold and the next fold, but hopefully we see what's happening as we fold it. Because now we can go into a table of values and see what that would look like. So 0 folds, there's 0 pieces of paper on top of each other, the thickness is 0.01. 1 fold, there's 1 piece of paper on top of each other. Then the next one, there's 2 pieces, 0.02. 2 folds, there are then 4 pieces of paper on top of it, or 0.04. 3 folds, that 4 pieces of paper gets folded, and there's 8 folds, 0.08 centimeters. 4 folds, 16 pieces. So now we're at 0.16. 5 folds, this is now 32 pieces of paper on top. So 0.32. If we want to continue this, 6, 7, 8, 9, 10, 11 folds. Right, so 32 becomes 64 pieces, or 0.64 centimeters. So we're almost at a centimeter thick. We fold it again, we get 128, so 1.28 centimeters thick. So now we've passed 1 centimeter after 7 folds. 128 times 2, we double it, right? Fold it over. 256 centimeters. So now we're at 2.56 centimeters, 256 pieces of paper. Again, hopefully you're starting to see a pattern. So 9 folds, we should be at around 5 centimeters. 10 folds, we have technically 1,024 pieces of paper on top of each other, so 10.24 centimeters. 11 folds, we're at 2,048 pieces of paper, or 20.48 centimeters. So again, you can continue this table, but hopefully you at least see an idea of now what we have to do to kind of figure out those predictions. So we can go back now and hopefully clarify or come up with more accurate predictions as we know, or now that we know how the piece of the thickness of the folded paper is changing. We can also go through and graph this to see what it would look like. So we have 0 and 0. 1 is basically very low. 2 is also very low. I'm going to say even till we get to a whole number roughly is about 7. We're at 1.2, so at 7 we could say we're about here. 8, we double it a little bit. We reach 10 at 10. You say it's almost something like that. And 11, we're now up to 20. 12, we're at probably about 40 because we doubled it. 13, we're at close to 80. 14, we're close to 160. 15, we're beyond what we see. So we can see kind of how our graph would look as well. So that is what our graph would look like. Does this look similar to any of the other graphs that we've looked at so far? Does it look linear? Does it look quadratic? Chances are you should probably say no, it doesn't look like either linear or quadratic. Right, quadratic might be close because we do have a curve. However, we don't see that U shape or that repetition, right? That similarity or that mirror image. Right, this starts off very, very, very low and then slowly gets higher and higher and higher and then starts to drastically take off. So you can use this type of relationship for what we see here to try to come up with answers for the previous questions about how many folds would we have to fold a piece of paper in half so that it reaches those heights. 15 meters, the 457 I believe for the CN Tower, folding it all the way to the moon. I mean, that's what, so this should give you the basis to kind of go through and answer those questions. And really what we're looking at is a new type of function which we call exponential functions. So we are going to learn about those a little bit later in more detail, but as long as you understand when things start to drastically increase like this, we're looking at exponential functions. But again, based off this table of values, looking at these models, you should be able to now go back and make more accurate guesses at how many times we need to fold that piece of paper.